that are linked to the energy transition. Of course, we will put them in the context of Africa. Those thematic are the renewable energy, battery technologies, hydrogen, ammonia, and in a broader context, we speak about the decarbonization. So please join me to welcome our distinguished speakers. I will start with Professor Abdel Faiq from UM6P, Dr. El-Ghali Bennouna from the Green Park Energy, Professor Ismail Sadoun from UM6P, and Professor Saeed Al-Asiri from UM6P. So please give them a clap. So can you please put the first slide of the presentation of Professor Faiq? So we'll start with the thematic of hydrogen session. So just a moment.
Can pass this slide?
Can pass the slide from here. Okay, so to introduce Professor Faiq, so he's full professor at UM6P, director of the LEMSET laboratory. He also serves as the R&D director at Innovate for Industry. He holds a PhD from the Basque Country University. He works at CNRS Orléans and the DELR, the German Aerospace Center. He joined as a group leader A.G.E.N.D.A in Vitoria, Spain, and he was awarded from the Basque Government Research Recognition Award. So please help me welcome Professor Faiq, please. The floor is yours.
Okay, thank you. I guess this one is working. Thank you, Mr. Chairman. Thank you for all of you for coming today to this session that we are going to speak about the energy transition in Africa, opportunities, challenges, and global impacts. As was introduced by the chairman, from my side, I will speak about green hydrogen. This is the topic of my talk. And just before starting, for the audience that are not familiar with chemistry, just to tell you that hydrogen is the first element in the periodic table that is composed by just proton and electron, and is composing, the name of hydrogen is coming from water creator, from the Greek words. Hydro means water, and gen is the creator. And you can see there that we have the molecule of the water is composed by one atom of oxygen, two atoms of hydrogen. But there is some confusion with these elements, because hydrogen is the element, just ash, that is having one electron. But when we speak about the gas, normally it's the hydrogen, but we call it hydrogen as well. This is the hydrogen gas that you can see here. And the hydrogen is the most abundant element in the universe. The equation that is rare to find it in pure form as a gas. All the time, the hydrogen atom is connected with other atoms. Even in our bodies, we have a lot of hydrogen. But all the time is connected with other atoms. For example, the case of the fuels, fossil fuels, you can see here like methane, butane. Ethane is composed by atoms of carbon and hydrogen. Why hydrogen is very important? Because can decarbonize almost all industrial sectors, can provide the needed electricity or energy, or can be used as well as a feedstock to produce other elements like fertilizers as well. The question today, if we are speaking about the current production of hydrogen in general, we are not speaking about green hydrogen yet, but just the hydrogen as a gas. We are producing, as you can see here, in 2023, the production worldwide, or global production, was arriving to 97 million tons per year. And from where we are producing this hydrogen? That's mainly from fossil fuels. That means we have 72 of this amount of 97 million tons is produced from natural gas, 22% from coal, 4% from oil, and we have just 2% that is produced by electrolysis in green process. What is the problem with the current production of hydrogen? Is the equation of the emission of CO2. Just to give you an idea, for each 1 kilogram of hydrogen that we produce 9.3 kilograms of CO2 that is thrown to the atmosphere. This is the reason why we should cut with the production of hydrogen based on fossil fuel and to look for a green process that can allow us to produce hydrogen. And among many green processes, we have the water electrolysis. That is the most promising technology. What means the water electrolysis? As you can see in this simple equation, that if we take the molecule of the water and we use electricity to break this molecule, we can produce hydrogen and oxygen. As you can see here, the feedstock of this reaction is just water. But of course, we need a source of electricity. And to classify this hydrogen as green hydrogen, we need a source of energy from renewables. This is like the condition. When we come to this technology of electrolysis, even that you hear that the equation is very simple, that just taking the water and to break it via electricity, but we have different kind of processes, and this is what we call the technology of alkaline electrolysis. That's the most mature technology and the most implemented technology at industrial level. We have the third technology that is called PEM, proton electrolyte membrane technology. And we have other emerging technologies like AEM in the middle between PEM and alkaline technology, and SOIC technology that is operating at high temperature. That means in the last process that you can see in the right side of the screen, we have SOIC solid oxide electrolysis cell that we need to have electricity as well heat, because this technology is operating at temperature between 700 and 1000 degrees C. Here in Morocco, we are speaking a lot about green hydrogen because, as you may know from the news, that we have many projects that are going on in Morocco to implement them. We have the one that's led by OCP Group. Why OCP Group is interested by green hydrogen or its derivative? Because nowadays the group is importing 2 million tons of gray ammonia, and we want to move or to shift from using a gray ammonia that's responsible of the greenhouse emissions to produce green ammonia in Morocco. And this is the reason in the roadmap of the investments of the group is targeting to produce 1 million ton of green ammonia in the horizon of 2027 and 3 million tons in 2032. And you can see that the budget for this investment, if we are speaking about this green roadmap of the group, we have a budget of $13 billion. More than half of it, $7 billion, is dedicated for green molecules in general. We are speaking about green ammonia, but also other molecules that we can produce from hydrogen. The second project is led by the government of Morocco, where they are looking to develop this new field of in Morocco, the green hydrogen and its derivatives. And recently was coming in the news that they accept 6 projects from 5 consortiums to invest around $32.8 billion. And you can see here the consortiums. Some of them are aiming to produce green ammonia in Morocco, but other ones that they are looking to produce green hydrogen to use it in the steel industry, and others that they are looking for other kind of e-fuels like green kerosene, green ethanol, green methanol, like the consortium of TAQA CISPA that are aiming to produce green ammonia, but also other e-fuels. But when we come to the development of this emerging field in Morocco and Africa, we have many challenges and opportunities. We can list here like the cost gap, because when we are speaking about the production of green hydrogen is a matter technology, but the question is the cost, still higher compared to the hydrogen produced from fossil fuel. These are like the main problems that we are facing nowadays. Also, we have the problem of water scarcity that when we speak about Africa and also Morocco, we have the off-taker who is going to pay the difference of the cost of this cost gap that wants to use green hydrogen or green ammonia instead of normal ones. We have also a research and development gap, limited local expertise, storage, transport, and other challenges that also we should target in the future, like public perception, policy, and the regulatory. When we come to the part of the research and development and innovation, when we speak about the current technology, about the electrolysis, for example, to produce green hydrogen or also other ones to produce other molecules, we still have a lot of things to do, like to advance manufacture technique in order to decrease the cost of the electrolyzer technology. We need to innovate in the part of the catalyst and material innovation. We still have a problem, even that it looks like very simple, but when we connect this electrolyzer with a source of renewable energy, we have the problem of intermittency. We should to deal with how to integrate the system with an intermittent source of electricity. And also we need to develop the next generation of the electrolyzers to decrease costs, or also sometimes we have the problem that some kind of elements, rare metals that we are using, or noble metals, that will have a shortcut in the future of the production of this kind of element. We should look for other technologies where we are not using this kind of rare metals. When we come to the value chain of the hydrogen, we are not speaking just about the production of hydrogen, but we should cover all the value chain from the feedstock, that means the renewable energy, or the water source, CO2. We have the question of converting this hydrogen to other molecules. That will be the topic of the presentation of my colleagues. How to handle also the hydrogen and transport it, how to convert it to electricity or to heat, and also some new industrial application of green hydrogen or green ammonia, a part of the fertilizer, but we have also new technologies, how to decarbonize iron and steel industry, or also to look for other industries where we can use hydrogen instead of the conventional fossil fuels. At the university, we are covering all these topics from different perspectives, and also looking for almost all the technology readiness level from 1 to 9. That means looking for material, new process and new material at the laboratory, to implement like a new solution in the laboratory. After that, to prove the technology in a living lab, and after that, to commercialize this kind of solution. That means system, to prove the system at industrial scale. When we come to Africa, Africa can play an important role in the development of green hydrogen and its derivative. Why? Because as I explained to you, we still have the cost gap between the green hydrogen and green ammonia. The green hydrogen production via electrolysis is an energivore technology. That means it's consuming a lot of electricity. This is the reason why we should look for a location where we can have a good quality of renewables and also a very competitive cost of renewables. And as you can see in Africa, we have many places that we have the combination between solar and wind. That means we can have a good quality of the renewable electricity without having like a sharp intermittency of the profile of the renewable electricity. Even in some areas that you see, we don't have good quality of solar or wind, but in these areas we have a good condition of geothermal. That means from renewable sources, we can have a good quality of renewable electricity that can allow us to decrease the cost of the green hydrogen to be competitive in the market. The question of the water also, when the people, they heard green hydrogen, they thought, okay, we are going to consume a lot of water in Africa. But here you can see in this slide that normally we are going to save water by the production of hydrogen via green process. But because, as you can see, if nowadays we are producing hydrogen by steam-methane reforming process, that means we are using methane with water to produce hydrogen, and we are consuming between 13 to 18 kilograms of water for each 1 kilogram of hydrogen. In the case of coal gasification, we are consuming even 4 times higher the amount of the water needed to produce the 1 kilogram of hydrogen. With electrolysis, we are saving water because just we are using the water that is used in the process to be cracked to produce hydrogen. And also, if we look to the expectation, nowadays we are consuming worldwide 90 million tons of hydrogen. If we look for the expectation in 2050 that we arrive to 500 million tons, the amount of the water will be needed to produce this quantity is 24.8 billion cubic meter, which is small in comparison with the water that is consuming in other part, like in municipal industries or agriculture. That means the question of the water is not a big problem when we are speaking about the hydrogen. But also, these are very important because when we speak about the cost of the desalination of the seawater is very marginal. We compare here that the energy needed to desalinate seawater is between 3 to 4 kilowatt hour per cubic meter. That means with a small impact on the budget of the production of each kilogram of the hydrogen. That means even producing green hydrogen can promote the desalination of the seawater and also can play a social impact. That's by providing drinkable water to nearby communities. These are very important points. For the education here at the UM6P, as it is a very new field also in Morocco in Africa, we are trying to cover in all levels and the type of education to integrate things related with the green with this field. Like when we are speaking about bachelors of science, we have integrated models, or also we have a lot of PhD students that are working in this field of hydrogen. But also we are organizing what we call executive training programs. And I will give you just an example of the Executive Master that we launched. The first one, the first edition was in 2023-2024. Second edition just launched this year. As you can see here in this Master Executive, we try to equip the leaders of today about the key elements, how to develop this new business in Morocco and Africa from technical point of view, from safety point of view, and also from business point of view. And for the experts that they were contributing with us in this master, we have experts from UM6P or from Morocco, but also we are able to count on more than 24 experts worldwide that they were coming to share their knowledge with the participants. Of course, we will be happy to host experts from these rooms. If you are interested to contribute with us in this Executive Master by lectures, just contact us and we will be happy to count on you in this venture.
Professor Fayek, could you conclude, please?
I will conclude. Just, okay. This is the first cohort that was graduated this year. That was composed by 53 participants, mainly from the main industries in Morocco working in this field or to develop this field of green hydrogen and green ammonia. This year, as I told you, we start the second edition. We have 30 participants. And this year also what was also having an impact, that we have also participants from Africa, from Tunisia, from Mauritania and Senegal, that they decided to come with us. And in the next edition, we'll be happy to host more participants from Africa. Thank you very much.
Thank you, Professor Fayek. Yes, our next speaker is Dr. Ghali Ben-Nouna. Dr. Ghali Ben-Nouna, he joined A.G.E.N.D.A in 2012 as a junior researcher in charge of thermal energy storage technologies and concentrating solar power. He took part in the creation of the Green Park platform. He holds PhD in physics from University Abdelmalik Saadi. And he will share with us what the Green Park is doing in renewable energy. Please.
Thank you, Professor, for this introduction, and thanks to the audience for being here. Today, I would like to share with you some thoughts from our experience at GEP concerning the energy transition in Africa, the opportunities and especially some challenges that we need to anticipate and to face to be successful in this energy transition. Well, needless to say, our continent is very rich in terms of renewable resources. So you can see here the map of wind speeds and wind potential for Africa, and you see that there is a lot of potential here. And you can also look for the solar maps, and you generally have a similar figure also for the solar part. And in addition to that, there is also the opportunity in terms of cost of energy. There has been tremendous drops of cost for solar photovoltaic and wind energy, and also for solar thermal, and nearly all of them are now competitive in many cases, and in most of the cases I would even say with fossil fuels, the exception being concentrated solar power, which is also dropping in cost and shall be soon, I believe, in the competitive range with the fossil fuels. This trend of decrease is continuing, though, so the costs are still dropping for most of the new renewable technologies. So the question is, if we have so much potential and the costs are so low, why don't we have photovoltaic farms everywhere and wind parks everywhere? The answer is that there are some challenges. So here in the figure on the bottom, you can see one of the challenges, which is called the capacity factors. Many of the renewable energies have a very low capacity factor that affects the grid. And speaking about the grid and the impact of renewable power on the grid, there are generally several transformations from the production or from the initial resource to the final grid. I've put here some example of these transformations, and the idea is that what you don't pay in the initial stage during the production or during the conversion, you have to pay it later at the grid level. So if we talk about the main two, let's say, parameters we need to talk about here, which is the cost of the kilowatt hour and the dispatchability, the dispatchability being the ability of one energy source to be controlled, to be adapted and adjusted depending on the need. So generally, when you have very cheap renewable energy, this energy is non-dispatchable. And at the opposite, if you see the example of the solar thermal, this is a dispatchable energy source. However, the cost is low. What you can do to have a better dispatchability, for example, with solar PV, and I think this is applicable for the wind also, is to have some storage, but then the costs go up. And this is something we need to pay attention to. I give you here just one example of what happened in California. Once they started injecting a lot of non-dispatchable renewables into their grid. So this is what you see here is the load curve of California during the days of March to May, typical days. So you have here the scale in gigawatts of necessary power, and you have here the time of the day. And you see that by the years, there is a pit that has been digged in the middle, and this creates a lot of problems for the grid manager and costs money to be addressed. So we have been speaking about power, but I have to draw your attention that there is not only power and electricity. The example I can show you here is in the industry. Most of the energy that is consumed in the industry is in the form of heat, and only a quarter of it is consumed in the form of power, electricity. And for that aspect, I come back to opportunities, and I have to talk about opportunities for solar heat for industrial processes. So here you have, for example, what we call the low temperatures, where you can have very basic solar thermal systems that can also compete with PV, solar PV systems with heat pumps. And we have also the medium temperatures, where you can have systems like the parabolic trough or Freenet concentrators that could do a good job. And by the way, for those types of systems, there are already a lot of projects that have been deployed in industries around the world, in China, India, in Europe, in the US, in Mexico. Unfortunately, not many in Morocco. You can go to this site ship plants, and you can have a clear idea about these projects. So this is something already competitive and a great opportunity for African industrials. What remains are the high temperatures. So for this, the technology is not mature enough, and here comes our role as researchers to work on developing new technologies for high temperature processes. I can give you here just the example of the company Synelion in Switzerland, who are developing high-temperature solar thermal systems for production of synthetic fuels for aviation, for example, and even for cement. And we at GEP are also now focusing more on this aspect because high temperatures processes can cover also mining, metallurgy, and many other industries that are already very strong and very present in the African context. And that was, by the way, the last opportunity I wanted to talk about. So that was it for me. I thank you for your attention. And I'll leave the floor back to Prof.
Thank you, Dr. Bennouna, for the insights. Our next speaker is Dr. Ismail Sadoun. He's full professor at Mohammed VI Polytechnic University. He completed his academic journey with a French PhD from the University of Bordeaux in 1992. Professor Ismail Sadoun, so he leads the electrochemical energy storage and conversion unit within ACER UM6P. He develops several of the key materials for battery from mineral resources, African mineral resources. He is key figure as well at EU, attracting EU projects. Please, the floor is yours.
Okay. Thank you very much, Mr. Chairman. Thank you all for coming to attend my short presentation. I was asked, this one is okay? Okay, I think it's okay. So I was asked by my chairman to fit in 7 minutes to present to you a familiar technology that you are using during chatting or during using Facebook or something like that. I'd like to talk about lithium-ion batteries. And I will try during this presentation, short presentation, to highlight, to emphasize the role of African mineral resource in the development of the next and actual generation of lithium-ion batteries. So, yes, let's start by this statement that now our energy source is more than 80% coming from fuel sources. And the world is very active for this energy transition to reduce the fuel cell and to use some clean energy sources like solar or something like that. Africa has no big footprint, carbon footprint, but we are asked also to do some effort for two big sectors. The first one is transportation. You know that transportation have a big CO2 emission, and also how to introduce some renewable energy in industry or building or something like that. But for these two technologies, mobile, like vehicles, and stationary, like solar energy storage, solar energy, we need to implement some storage solution, efficient storage solution. And batteries are really now the best choice to store energy for mobile and stationary application. So let me do some explanation how the battery is working when we are calling or when you are charging your battery in the sector. So the battery, I don't have a printer, but the battery is composed from two electrode, positive electrode and negative electrode. And during charge process, we have lithium moving from the positive electrode to the negative electrode. So it's just lithium ion moving from one side to the other side. That's why we call it lithium ion batteries and not lithium batteries. It's lithium ion batteries. And during discharge, we have the reverse phenomenon. Lithium ion are in yellow are coming back from the anode side to the cathode side. And the number of exchanged lithium give you the capacity. And the capacity means the time that you are charging or discharging the batteries. And the kinetics of transferring lithium from one side to the other side give you what we call power, is the time of charging or time of discharging. So lithium-ion batteries are used in many applications. You can see here a lot of applications from some small smartphone, laptops, and even in medical science, but also in some bigger applications like storing energy storage, or like in vehicles or aircraft or something like that. The principle is the same. The principle of charging and discharging the battery is transformation of chemical energy to electrical energy and vice versa. And the market, here I show some market, there are billion of dollars of markets in now and in the future. And they are changing day by day in the positive way. But now I would like to emphasize something. When you buy batteries, and you see here in the down side of my slide, more than 30% of the cost is coming from the cathode side, cathode material, and 10% from anode side. So the business of the lithium-ion battery in the future is from the cathode side. Okay, what are now in the market as cathode side? If you Google battery, you can see you have battery LFP, battery NMC, or battery NMC, and NCA. Battery LFP, for instance, is called because the cathode material is lithium iron phosphate, lithium L iron F phosphate P, LFP. And you see we have lithium like 70%, we have the graphite is the most used anode material. We have NMC, and like nickel, and like manganese, and say like cobalt. And we have this 532 or 111 is the proportion of each cathode, each element. For instance, NMC 111, we have 1/3 nickel, 1/3 manganese, 1/3 cobalt in the cathode side. And at the end. And the left part of my presentation, this is the Google map where we put the strategic minerals available in Africa. Of course, you can see, I don't know if you can see here, we have, of course, in Morocco, a lot of phosphate, as you know, but we have all needed minerals in Africa. Cobalt, nickel, manganese, graphite, lithium, everywhere. So we can be really the strategic continent that will be the key to develop next generation battery. Of course, there are a lot of opportunities, a lot of challenge of lithium-ion battery, like a cost, energy density, safety, and also recyclability and predictability. But this is really a very challenging course to the best lithium-ion batteries. Yes, the problem is we have a supremacy of China, of course. Why? Because China came to Africa before and then extract some raw minerals and then transform these minerals to high-value elements. So if you see here the repartition between China, European Union, and others, from mining, graphite, we have China, but for lithium, manganese, nickel, is others. Others means mainly Africa. But during the treatment, production, and battery, you see at the end, we have only Chinese. So China have really great advance in battery or cells manufacturing. Morocco start to attract a lot of gigafactory, as you know. We have now, but they are mainly Chinese, of course, because the expertise of China is very, very important. We have some gigafactory in the north, in Tangier, where they are working graphite. We have Goshen with the Moroccan region, where NMC, remember NMC, and we have TNC and COBCO working with OCP on LFP cathode materials. So we can ask why gigafactories are coming to Morocco, because Morocco is the bridge between Africa, where we have the raw material, raw minerals, and Europe, where a huge number of batteries are needed in the future. So there is an urgent need to develop educational program to transform the raw material from Africa to high value. That's why I would like to introduce very briefly that we are launching 2 years ago an engineer courses to develop process in chemical process, mineral process, and battery process to transform the raw material to high value for application in battery, but also in other sectors. So I'm done. Thank you very much for your attention, and back to you.
Thank you, Professor Sadoun, for the key insights and also for respecting the time. So the next speaker is Dr. Saeed Lasiri. He's an assistant professor in heterogeneous catalysts at Mohammed VI Polytechnic University. His current work focuses on designing novel catalysts for ammonia production as a green energy carrier and converting CO2 into high added value. So, Professor Lasiri, so you can continue.
Thank you very much, Professor Abdel Ghafour, for this kind introduction, and thank you all for being here for this talk, which I will be briefly introducing some of our work on the development of catalytic processes for green ammonia production. I will take such few slides to introduce the importance of ammonia, why we are working on that, Ammonia is a very important molecule in the preparation of nitrogen-based fertilizers. So in this figure, we show that starting from 2000, half of the humanity will have been dependent on our capacity to produce nitrogen-based fertilizers. So it's a very important molecule that sustains half of the population. Unfortunately, fertilizers utilization in Africa is significantly lower compared to total developed countries, which affect, of course, intensive agriculture in Africa. We are also interested in ammonia not only as a nitrogen building block for fertilizer, but new applications are emerging in the energy sector. Actually, what we are showing here is that ammonia have a decent volumetric energy density that is compared to methanol, so we can use it as a direct source for energy. We are also showing in the right graph that show that the ammonia is the lowest cost option for energy transport over long distances. What you have seen in the previous presentation, we can, of course, transform the renewables into hydrogen that we can use for energy generation. But to transport this hydrogen where it's going to be consumed, it's much more cheaper to transform it first to ammonia and then ship it where it is needed and then decompose it back to hydrogen and utilize it. So how do we produce this ammonia at the industrial scale? It's via the Haber-Bosch process, which is well-known process for ammonia generation from nitrogen coming from air, and hydrogen coming now from fossil fuels, mainly natural gas. And these two molecules are combined on a catalytic process that operates at very high energy consuming condition. The temperature is between 400 and 500 degrees C and the pressure above 100 bar. The results of such a way of producing ammonia, of course, is that the whole process consumes almost 2% of the world's annual energy demand. It's only viable because of the economy of scale. Actually, the Haber-Bosch there are very few units in the world that very much centralized, and they are close to where natural gas is available. More importantly, for each ton of ammonia that we produce via the Haber-Bosch process, we generate at least 2.3 tons of fossil-derived CO2. So there is an urgent need to decarbonize the whole process for ammonia generation. I will be showing the same graph that my colleagues have shown as well. As for Africa, there is an abundance of renewable energy. These two maps shows the potential of solar energy in the African continent, but also the wind speed distribution across the continent. So we see a nice mix between the two. And there is also that the levelized cost of energy derived from renewables is now being competitive with the energy derived from fossil fuels. So that opened the door for integration of renewable energy and ammonia synthesis process, which then can decarbonize the whole fertilizer industry footprint. How this is possible? So in green ammonia production, the main issue is related to the utilization of hydrogen. So with the utilization of electrolyzers, we can crack water directly into hydrogen that we can use for the Haber-Bosch process. And nitrogen, we can just directly mine it from air. Of course, it's only green if it's fuel with the renewables. And that will allow us to decouple ammonia production from hydrogen derived from fossil resources, but not only hydrogen and ammonia, that can also be applied for different green molecules such as methanol, methane, etc. And it also allows us to think differently about chemical production. So we can now start thinking about delocalized production in a distributed, sustainable way where renewables energy are available. But for that, we have to develop agile system that will allow us to produce molecules on site and on time when it is needed, versus what we have now, which is mass production, transport, and storage. So how can we do that for ammonia? There are several challenges. We are more focusing on the catalyst part. The whole technology is still under development. In the catalysis part, where a catalyst will accelerate the reaction between hydrogen and nitrogen, we lack catalysts that are capable of operating under intermittent condition. What you want to do also to bring the cost of green ammonia down to be competitive with what we have now is to develop catalysts operating at lower pressure and lower temperature. The pressure should be aligned with the pressure that electrolyzers can deliver hydrogen. So this will avoid unnecessarily pressurizing the system to higher pressure. Of course, what we are developing now are catalysts that also can be resistant to new poisons such as water and oxygen. The cost should be competitive with the industrial Haber-Bosch process catalyst, which is iron-based, and we should be able to scale up any catalyst that we are producing in our labs. So I will briefly introduce some of the families of materials that we are working on this in our laboratories at UM6P. So we are working different materials such as nitride materials, electride materials, and 2D materials, which shows high potential for for ammonia, green ammonia production at mild condition. Generally are active between 300 and 350 degrees C and pressure, which is around 50 bar. I will just conclude with showing some experimental results from our lab, showing that we have been able to develop catalytic materials that are 25 times higher than the industrial actual catalyst, and that could potentially operate at low pressure and low temperature, which opened the door for delocalized ammonia production. And in my left, there is 2D materials that are active at temperature that's starting from 300 degrees C, which was so far unprecedented in the literature. So with this, I would like to thank you all for your attention. Thank you.
Thank you very much, Professor Al-Asiri. So while letting you preparing your questions, I will just take a round of one question per speaker, and then we take the question from the audience. Let me start with the last one, which is the ammonia, which is still fresh in your memory with Professor Al-Asiri. So you have provided a key insight on the role of ammonia in the energy transition now and the decarbonization. So do you see a need to replace the well-established Haber-Bosch process to enable this widespread deployment of ammonia in this new energy system?
Well, thank you for this nice question. Do we need to replace the whole process with new processes? I think for the moment, it's the ammonia loop doesn't distinguish really between gray and green hydrogen. We have more work to do in reactant production, decarbonizing the whole process from a point of view of hydrogen production, and work on developing catalysts that will match the pressure coming from the electrolyzer. So it's more retrofitting than engineering new ways for ammonia production. The Haber-Bosch is very well optimized. It produced the ammonia at the lowest cost possible, lowest cost in terms of energy as well. So what we need to do is retrofitting to be able to work with intermittency condition and at lower pressure, lower temperature, but it's still a new optimization of what we have now.
Thank you, Professor Al-Asiri. So, Dr. Ghali Bennouna, so you mentioned in your slide that dispatchability is a big problem actually in California. Do you see such a challenge to happen as well in Africa, and how to deal with such a challenge in the energy transition?
Yeah, thank you for this question. Actually, this challenge is for every country. In the case of Morocco, we did not reach this situation that I showed you in California, because our grid operator, O.N.A., have, I would not say alerted about this risk, but they anticipated it, and among the action that they did is that they try to restrict a little bit the integration of new renewable capacities in the grid. So people were wondering why can't we just simply have new solar plants and connect to the grid? That's maybe one answer for those of you who might ask this question. And in parallel, they have developed storage capacities, hydro storage capacities, and additional dispatchable power capacities to compensate for that. And the main dispatchable capacity I'm talking about is natural gas, is open cycle gas turbines. So we have, at least to my knowledge, 2 projects that will come soon to realization, one in Wazan and one in Nador. And I think this shall apply also to Africa. If the intention is to deploy large capacities of non-dispatchable renewables, you need in forehand to strengthen the grid, to foresee storage capacities, and to invest in dispatchable capacities. And I think Africa has also the necessary resources for those type of dispatchable capacities.
Thank you, Dr. Bennouna. Professor Sadoun, so you have lots of activities in Africa, basically, and then I think you have a good overview of what happens in Africa for the mineral resources. What role does Africa currently play in the global supply chain of lithium and other critical battery minerals?
Okay, thank you for this critical question. Of course, as I tried to emphasize during my presentation, in Africa we have almost all raw material that are needed for battery development. We have, for instance, in Morocco, we have a huge quantity of phosphate, as you know. We have huge quantity of phosphate. We are the first producer in the world. We have in Mali, for instance, or Zimbabwe, huge quantity of lithium. RDC, the Congo, have more than 50% of cobalt. And we have also Madagascar with graphite. So we have everything to do. South Africa, manganese, for instance. But the problem is, as I said before, the raw material here, but they are refined elsewhere. Except Morocco have this outstanding approach. OCP, for instance, are transforming the rock phosphate to phosphoric acid that is used directly to LFP. And we have also managem. We have some small quantity of cobalt raw, and they are transforming to cobalt sulfate and so on. And this is really the reason why some gigafactories are coming to Morocco, because we are producing some minerals, but also they are transforming these minerals to ready element to be introduced in the battery manufacturing.
Interesting, thank you. Professor Faiq, so you lead the large program on green hydrogen at UM6P. What role do you see for African universities in driving faster deployment of the hydrogen economy in Africa through R&D?
This is a very important question that we need to answer, because when we start speaking about this new field or emerging field, we should first prepare the leaders of tomorrow. This is the reason why we should start by some high-level programs to equip these leaders by the skills to be or for the well development of this new technology. Because when we are speaking about hydrogen, we are also having the question about the safety as well, and the choose of the technology and so on. That means these are the first things. But after that, when we implement these kind of factories in Africa that dealing with this new business of green hydrogen and its derivatives, we need to have the people that are working there to operate these facilities. Also, we need to design like training and formation that will help these people to well manage this new technology in Africa. And then later on, we have the part that is very important. We should not stop here, because this market, we should have some decrease, significant decrease of the cost. That the role of the research and development is very important. We should to develop our own technology that can be adapted to the context of Africa, the condition of Africa, and that will allow to decrease the cost of these new molecules or green molecules that we are speaking. And also just not the production of these molecules, but also the business connects with these developments. Because as I mentioned before, green hydrogen, nowadays we have like a very clear application at industrial level, but the future that we can apply these kind of molecule in other industries. That's also we have like some kind of plan to decarbonize other sectors like steel factories or other kind of industries. That means also in this part we need to develop research and development how to use these new molecules in other sectors, in other fields where we have lots of emission of CO2 and we can decarbonize this kind of industry. This is the reason why, as somebody that the education information is a very important point, but research and development should be as well starting nowadays to answer to the question of tomorrow.
Thank you, Professor Fayek. So I open the floor to the audience. So Professor A.G.E.N.D.A. Okay.
Thank you very much. That's my main message. I don't have a very specific question. I must say, just as the theme of the conference, as you see, is shaping the future of higher education, innovation, and all that. And I think this is it. We are already in that future. This is just to say how proud we are at UM6P. I think we need at least one, if not more, specific conferences on these themes. Because we are in the heart of the engine. As we're talking about the future of the continent, energy, renewable materials, decarbonation, green ammonia, green hydrogen, I think I hope that through this, although the room is not full because we are concurrent sessions, my main message and question to you guys is the challenge is huge for the continent. And UM6P is of course positioning itself today as a hub for bringing this technology, but how far have we gone in developing the partnerships across the continent for getting this done? Because this is not a one university or one institute job. This is the job of the whole continent. So I'd like to hear from you, what's your view on developing these partnerships? Thank you.
I will just, very briefly, I will just to answer to this question in a way that, as I mentioned before, that at UM6P, we have nowadays more or less 1,000 PhD students. And officially, we have 19% of these PhD students are from Africa. This is like how we can start, because these people that we are forming nowadays, tomorrow we will be our ambassadors in Africa. This is the first point. Second point, as I mentioned in our existing master, we are doing a lot of effort to attract participants from Africa. We reached this year to have participants from Tunisia, Senegal, Mauritania, but we will love to have more participants from other parts of Africa. Partnership, we are coming to this. Thank you very much, Siraj, for organizing these events here in Morocco. We need to have more active participation from our side to show that we are willing to develop this South-South collaboration. This is our aim. This is why we are today here, and we are open to collaborate. We start many discussions in the past, but unfortunately, sometimes when it is missing to have like a funding opportunities, like making a big barrier to continue in this kind of collaboration. We'll be happy through this conference if we find some clear pathway how can help us to have a funding support that can allow to our partners to be involved with us in this kind of collaboration, but we are open to have it.
So you said everything. Yeah, thank you, Siraj, for your kind words. Of course, the link between Morocco and Africa is through two sectors. One is education, of course, and Samad told about some PhD students, but we have also this engineering program. And each year we have like 10% of African coming to follow this engineering program. So it's good ambassadors for Africa to make the bridge between Morocco and Africa. And there's also some call between African Union and European Union. And this core of project involve universities from Africa and universities from Europe. I can talk about one big project that we got like 10 million euros, CESA, Smart Energy Solution for Africa, and where we implement some demonstrator in Morocco, for instance, that will be duplicated in Africa. like photovoltaics, battery, biomass, and so on. So there are some recent call of project to make this partnership between Morocco and Africa, and I think there are some activities that are coming in the future, inshallah. Who would like to talk?
No? Dr. Hisham, do you have...
Good morning. My name is Hisham Gourg. I'm head of Technology Transfer Office here at UM6P. Thank you very much, professors, for delivering these very important and valuable presentations. You are covering the most important part of energy transition in renewable energies, actually. And as pointed out by the president of the university yesterday in his talk, the main reason of the creation of this university is to develop sovereign technologies to serve Morocco as well as Africa. And I have one question, and it has two parts on it. The first part is covered by Rashid Sarrej regarding the collaboration with other African universities. And the first one is, how do you collaborate together? You are covering different aspects of this subject to develop a technology that, or technologies that can be 100% developed by you, collaborating together. Thank you.
Very good question, Dr. Gourg. Who wants to answer? Okay. Sure, nobody wants to answer. Okay, so let's say, so we have, of course, it's multidisciplinary anyway. You see here that there are different aspects of different thematics that we work on. So basically, the multidisciplinarity is there. If I speak personally, I don't know what the other ones are doing. So there is, of course, with the colleagues, I collaborate with Saeed directly. I collaborate with Ismail Saadon. So we develop things. I am doing the process part. They are doing the material part. So such thing is a win-win situation that exists. Of course, the floor is open to others. Of course, several discussions with Abd Samad as well on earlier. We haven't put up things together, but things are going on. So we submit patents. You know that you are the head of TTO. We submitted patents. We start from very early stage development of the technology, but we have approaches that we apply. We call them the top-down approach, where we can assess the technologies at very early stage, how it will behave and how it will perform in terms of key performance indicator at large scale before we start really developing into the direction in which it will be developed. So if someone would like to add something, we... No? Another question? Yeah, if not, we are sharp 1 hour. So I would like to thank everyone for being here and thank our distinguished speaker for giving us the time and the key insights about what they are doing. Please give them a clap and we close this session.